All right, guys, today we're going to cover Chapter 1, Part 4, Extrema and Average Rates of Change. Okay, so first some definitions. So for a function to be increasing, that means the rate of change is positive. So this indicates a positive rate of change. And you can think about that as an upward slope. And then decreasing is a negative rate of change. And you can think about that as a downward slope. And then constant is a zero rate of change. You think about that as a flat slope. So when we analyze a function over any interval, we should be able to determine if it is increasing, decreasing, or constant. And then a maximum is the highest point for the function. Minimum is a lowest point for the function. And then the term extrema means either a max or a min. So a maximum or a minimum is an extrema. And then the average rate of change. So this is the slope of a function for a given interval. Of the domain. So the average rate of change would be the average slope of that function for a given interval. So you're going to be between some A and some B. A secant line, this touches 2 points on the graph. So if I had, I don't know, let's say this sort of graph, and I was interested in its average rate of change between these 2 points, the secant line between those 2 points would have that average rate of change. So it's secant line and average rate of change are related, and it touches at least 2 points, it doesn't necessarily preclude the possibility that it touches more, but it touches at least 2 points. And those 2 points in the case of average rate of change would be the beginning and the ending points of that interval of the domain that we're concerned about. So here are some graphical examples of increasing, decreasing, and constant. So if you look at this first one, we see this function has an upward slope, and so it is increasing. And if we're concerned about the interval x1 to x2, you see it's clearly increasing on that interval. Here we have decreasing behavior between x1 and x2. And here on the third example, we have horizontal or zero slope constant behavior between x1 and x2. So let's analyze the behavior of a function. So you've got f of x equals x squared minus 4, and it says to the nearest half unit. I don't like that. We'll just go to the nearest unit because the half unit thing is confusing. And they're inconsistent about which way they round and so on with their answers. So just to make things simple, we'll go to the nearest unit, not half unit. Okay, so first of all, it appears to be decreasing from negative infinity to 0, and then increasing from 0 to infinity. So I'm going to say from negative infinity to 0, it is decreasing. And then from 0 to positive infinity, it is increasing. So we describe two intervals of behavior. Decreasing from negative infinity to 0, increasing from 0 to infinity. All right, let's look at this one. So here we have negative x cubed plus x. And we've got 3 intervals of behavior here, it looks like to me. So, yeah. In this case, it does make sense to go to the nearest half unit because these clearly occur at negative 0.5 and 0.5. So what I've got is behavior negative infinity to negative 0.5. It looks like it's going downward and decreasing. And then between negative 0.5 and positive 0.5, it appears to be increasing. And then 0.5 to infinity, decreasing again. So let's write all that out. Negative infinity to negative 0.5 appears to be decreasing. From negative 0.5 to 0.5, it is increasing. And then from 0.5 to infinity, we're decreasing again. That should be consistent with my abbreviations here. Okay. Decreasing, increasing, decreasing. Moving on to part C. Well, actually, this is one for you guys. So see if you can figure out, and forget about this half unit for this one. Just estimate as best you can. You know, it doesn't have to be to the nearest half unit. Just give me your best estimate. So you're going to have 2 intervals of behavior. And when I know where it's coming from, where it's going to, and what that behavior is. So pause the video, see if you can figure this out, and then start it back up and see if you're right. Okay, so let's figure this out. Again, the whole half unit nonsense is confusing here. But that looks to me like about negative 0.8. So I'll estimate it to be that. So negative infinity to negative 0.8, it's going downward or decreasing. And then negative 0.8 to positive infinity, it's going upward or increasing. And if this number is slightly different on your paper, that's okay. Again, that's an estimate. I wanted an exact value while we find the vertex and so on, but that goes beyond the scope of this problem. This is all about graphical analysis and estimation. Relative and absolute extrema. So here's an important one, and one that's often missed on the quiz and the test. So relative extrema are extrema over a portion of the domain. So do you see how this is a highest point, but not the highest point? So this is an example of a relative max, and this is an example of an absolute max. So a relative extrema, relative max or min, is a max or min over some portion of the domain. An absolute max or min is the highest or lowest point anywhere on that function. So relative is a max or min for a subset of the domain. An absolute max or min is a max or min everywhere. There is no higher or lower point. And so once again, here you see a relative min, because it's a lowest point, but it's not the lowest point. And then an absolute minimum. There is not point exactly where it needs to be. There we go. Okay, so estimate and identify the extrema of a function. So estimate and classify the extrema for this function, and then support your answers numerically. So we would want to first look at the graph, make our best guess, and then we'll use the calculator to see if that guess was accurate. Okay, so first of all, looks like a relative minimum here and a relative maximum here. And I say relative because there are lower points elsewhere and higher points elsewhere for that min and max. Now this is indexed strangely. It goes by 2s on the x-axis and by 4s on the y-axis. Not a good practice. Makes it very confusing. But that looks about like, I don't know, negative 1.5. So at about, we'll say a relative max, relative min. We'll do that one first. Relative min at about x equals negative 1.75. That's my guess. And then, and that's this value. And then a relative max at about x equals 2. So those are my guesses. And let's see how close I was by using the calculator. So if we punch this function into our calculator, it's going to take a second because that's a lot of terms. Negative x to the 5th plus 2x to the 4th plus 3x cubed minus 4x squared plus 3x. And then a graph on the standard window, so zoom 6. It'll be a little different because this goes up to 16, but yeah, we'll need to go up a little higher. So let's change the window to have a Y max of 16. There we go, that captures the min and the max well. So in order to find minima or maxima on your calculator, second and trace brings up the calculate menu. If I go down here, I see two options, 3 minimum and 4 maximum. So let's choose the minimum first. And it asks us for a left bound. So the calculator here is asking us, where do I start looking for this minimum value? So let's start looking. We definitely want to go to the left of it. I can navigate like so. So that's plenty to the left of it. Enter, and then right bound. So it's asking, where do I stop looking from left to right for this minimum? So we're going to navigate to the right of the minimum, and then enter, and enter. And it tells us it occurs exactly at negative 1.23. So graph was a little difficult to tell. So it happens exactly at negative 1.23. So my estimate was fairly close, I guess. And it is negative 7.9. So to the nearest 10. And so this is going to be the point. Let's go negative 1.2 and negative 7.9. So that's a relative minimum of this function. Now the maximum. Let's see how close I was. Second and tracing in option 4. Where do I start looking? Well, let's start looking at positive 1. Where do I stop looking? Let's stop looking at 3. That will certainly capture it. So it's 2.15, 2.2 if I go to the nearest 10, and then 14.6. So that point is 2.2 and 14.6. Again, rounded to the nearest 10. So we guessed by looking at the graph, and because of the indexing and the imperfect graphing, our guesses were a little off, but we checked them in the calculator and we found these are the exact values to the nearest 10 of the minimum and maximums here. So here's one for you. Do the same thing. Let's see if I can get that just a bit bigger because that's tiny. I'll rewrite that function. F of x equals x cubed plus 3x squared plus x plus 1. So see if you can find, estimate the extrema, and then find them exactly. Pause the video and then can. Okay, so I'm assuming you're back. First of all, it looks like a relative max. And it looks to me like that occurs at x equals negative 1. And then a relative min right here. So relative min at about x equals negative 0.2 or something, just less than 0. All right, let's put it in our calculator and see. So I go to y equals, clear out whatever mess is there. X cubed plus 3x squared plus x plus 1. And if I graph this, I'll see those 2 points. So second trace, maximum. Be careful here because I don't want to capture any of these points over here that are higher. So left bound, let's go -3. And then right bound, we'll go -1. That'll capture it without getting any of those higher points and confusing the software. So it's at x equals -1.8. This was a guess, and this is to the nearest tenth, the exact value. And then the y value is about 3.1. And then for the relative minimum value, second trace, option 3, start at -1 and go to +1. It's -0.2, so for once I got it right. And then y equals 0.9. So these were my guesses. Yours might have varied a little bit. That's okay. And this was to the nearest tenth. Those extremist values exactly, an x and a y, a point on the graph. Okay, moving on. Using a graphing calculator, which we've been doing to support our answer anyway, approximate the nearest to the nearest hundredth, the relative or absolute extrema of, and they give us a function. No graph this time, so you have to use your calculator. Can't do any estimation first. Okay, so let's go to y equals, clear out whatever's there. Function x to the fourth minus 5x squared minus 2x plus 4. And if I get graph, I'll see, looks like a relative minimum, a relative maximum, and then an absolute minimum. So we haven't encountered one of those before. So we've got a relative min, a relative max, and then an absolute min. Let's find their location. It says to the nearest thousandth. So second trace, minimum 3 is what we're going to do. Let's go to -2 and then -1. That'll capture it without a lot of extra stuff going on. So to the nearest thousandth, so it's tens, hundreds, thousandths, that's this digit. That would be -1.470. The x coordinate. And then 0.805, the y coordinate. And then for that little relative max, second trace, option 4 this time, start it to -1, go to +1, and capture it. So that's -203, -0.203. And then for the y value, it is 4.202 to the nearest thousand. Now the absolute minimum value is over here, second trace, option 3, start at +1, go to +3. And I have 1.673. And then the y value is -5.507. To the nearest thousand. You know, and there is some argument about which way you round negative values. I just keep it simple and round both the same way, you know, away from 0. But, you know, you might find some argument about that somewhere. If so, you feel free to mention that to me when we're in person class. Okay, here's one for you. Do the same thing. Use a graphic calculator to approximate the extrema and state the x values where they occur. All right, pause the video and do that. Okay, assuming you're back, so let's punch this expression in. I've got y equals, clear out whatever's there. You've got x cubed plus 2x squared minus x minus 1. So graph that, and it looks like a relative max and then a relative min. So we're going to have an x value and a y value for those. Second, and trace first 4 for, well, actually, let's do the maximum first. Yeah, that's 4. Okay, so -2 to -1, we'll capture it. And there it is, -1.5, and we're going to the nearest hundredth this time. So that's the second digit after the decimal. -1.55. And then for the y value there, it's 1.63. And then the relative minimum, second trace, option 3. Start at -1, go to +1. That will capture it. And that lowest point is 0.22 on the x-axis to the nearest 100, 0.22. And then for the y, -1.11. Okay, so that's what you should have got. Moving on to example 4, using Extrema for optimization. So this is really where mathematical modeling is powerful, because you can optimize a situation. So advertisements for a new car claim that a tank of gas will take a driver and 3 passengers about 360 miles. After researching on the internet, you find that the function for miles per tank of gas for the car is the following. It gives us the expression, where x is the speed in miles per hour. What speed optimizes the distance a car can travel on a tank of gas? So in other words, what is the maximum of this function? We're searching for the maximum. So we'll graph it on the calculator and find that maximum value. So we punch in -0.025x squared plus 3.5x plus 240. Okay, so now we need to be careful with our window. So 360 miles is what you should expect. So I would expect my y values to be around that. So let's go from, I don't know, 0 to 400 on the y, and then speed is the x. So let's go from 0 to 100 miles an hour. So once again, the x values will go from 0 to 100, because those are the most reasonable constraints for speed. And then in miles per tank, let's go from 0 to 400. And we'll adjust as necessary. So that's a pretty good graph, and we clearly see the maximum value here. So if I use the maximum function, left bound, that's pretty a good choice there. 50 is well to the left. And then, I don't know, like 90, be clearly to the right of it. So it appears to happen at 70 miles an hour. So what speed optimizes the distance? This first question. The answer, as a consequence of our graphical analysis, is x equals 70. And how far will the car travel at that speed? 362.5 miles. And remember, this is in miles per hour, the x value, and then the y value is in miles. Okay, so here's a fun problem. This is one, you'll see this on the ACT a lot. You'll see it on intelligence tests a lot. It's a pretty fun little problem. Really challenges your spatial intelligence. So you have a square with a side length x. So in other words, they're cutting a notch out of it. And then they're folding that to form an open box. So think about if I folded along these lines, you see I would have a shallow little box. So we're cutting away that corner and then folding along these dotted lines. So the result is a box that has length, we'll call this one length. So that's going to be 8 minus 2x, because we cut out the x here and here. And then the width, we're going to call that 12 minus 2x. Once again, we cut out the x here and here. And then the height will just be x. So this is going to be 8 minus 2x times 12 minus 2x times x. So that's going to be our volume function. And what x value is going to maximize our volume, make our box as big as it could possibly be. So once again, we're going to go to the y equals screen, and let's punch in our equation that we developed. And you don't have to multiply this out. You can put it in exactly as it is and save yourself some time. 8 minus 2x, and then 12 minus 2x, and then x. So length times width times height finds the volume. Here we analyze the graph, or the figure, and determine the length, the width, and the height. Okay, so let's be cautious about our window again. So we're 8 inches is our smallest side. So do you see how 4 is the most we could ever cut out? We could never cut out less than 0, and we could only ever cut out 4. We'd be cutting out an entire half of a side. So 4 is a maximum that's not included. 0 is a minimum that's not included. So those make sense for our x values. And then for the y, well, I'm not sure about the volume. Let's just go with what we've got here and see what that looks like. We clearly got a little too much y, but we can see the maximum. So let's second trace, find 4, the maximum. Left bound, let's start about 1, and then let's stop about 3. So about 1, and does it give us a direction on rounding? It says determine the length and width. Okay, so we'll just go to the nearest hundredth. X equals 1.57. So that would mean that's optimizes. So that's a max volume. But we don't want x, we want length and width. Remember that the length equals 8 minus 2x, and the width equals 12 minus 2x. So once we find that x that optimizes, we can plug it into these expressions and find our length and width. So 8 minus 2 times 1.57. It's about 4.86. And then, and I use approximately equal to because we rounded earlier. So 12 minus 2 times 1.57 is about 8.86. So there's the length and width to the nearest hundredth that will maximize our volume in this case. Okay, average rate of change. Now, I often warn students about problems that are frequently missed on the quizzes or tests. This is just such a problem. So average rate of change problems missed disproportionately to the other problems on the test. Make a mental note, and when you study for the test, you're going to spend a little more time on this, is my advice. Okay, so basically, you're gonna take a point, x1 is where you're gonna start your analysis, and x2 when you're gonna end your analysis. And we just plug those into the slope formula. That's all this is. Those 2 points go into the slope formula. So here we have a function. So we have negative 2x squared plus 4x plus 6, and we're concerned about this interval. So this is our x1, and this is our x2. So remember that it's x1 and then f of x1. That's the first point, and then x2 and our f of x2. Once we have those values, we're going to plug them into the slope formula, which is going to be m equals y2 minus y1, which is the rise, over x2 minus x1, and that's the run. So first, let's find f of x sub 1. So that's negative 3. So if I plug in negative 3 into the function, we get negative 2 times negative 3 squared plus 4 times negative 3 plus 6. And so that's negative 2 times 9, remember PEMDAS, minus 12 plus 6, negative 18 minus 12 plus 6, negative 30 plus 6, or negative 24. So our first point is going to be negative 3 comma negative 24. Now let's find our other point, x sub 2, and then f of x sub 2. So that's going to be negative 1 comma f of negative 1. And so if I find f of negative 1, that's going to equal negative 2 times negative 1 squared plus 4 times negative 1 plus 6. So that's negative 2 times positive 1. Again, minus 4 plus 6. So negative 2 minus 4 plus 6. Negative 6 plus 6, or 0. So I have, this point is going to equal negative 1 comma 0. Now we're ready to plug those into the slope formula. So we've got our 2 points. We've got our x1, y1, and our x2, y2, and we're going to plug those into, again, the slope formula. So y2 is 0 minus y1 is a negative 24 over x2, which is negative 1, minus x1, so minus a negative 3. So that's 24. Negative 1 minus a negative 3 is negative 1 plus 3, and so that's 2. And so it is a slope, an average rate of change for the function between those 2 points is positive 12. So that makes sense when you think about it, because it goes from negative 24 up to 0. So it's going 12 units upward per point on average. It's quadratic, so it wouldn't be linear, but that's the average rate of change, 12 units over this interval. If I picked different x1 and x2 values, that answer would be different, because the slope of this function, again, is not linear. Okay, moving on. Once again, average rates of change. So we're given our x1 and our x2 here, and we want to find x1 comma f of x1. That'll be our first point. And then x2 comma f of x2. F of x2. So This is going to be 2 comma f of 2. And this is going to be 5 comma f of 5 for this point. And here I have f of 2 is going to equal negative 2, the same function, times 2 squared plus 4 times 2 plus 6. So that's negative 2 times 4 plus 8 plus 6. So that's negative 8 plus 6, or just 6. So this point is 2 comma 6. And then, let me shrink this down a little bit. Over here, I want to find f of 5. So that's negative 2 times 5 squared plus 4 times 5 plus 6. Negative 2 times 25 plus 20 plus 6. So that's negative 50 plus 20 plus 6. Negative 30 plus 6. Or negative 24. Okay, so that point is going to be 5 comma negative 24. Now we've got 2 points to put into our slope formula. This is our x1, y1. This is our x2, y2. And remember that m equals y2 minus y1 over x2 minus x1. One of the few formulas that's really worth remembering. So y2 is negative 24 minus y1, which is 6. Excuse me, over x2, which is 5, minus x1, which is 2. So that's negative 30 over 3, or negative 10. So, as I said earlier, the rate of change will be different over different intervals for this function. And here we see it was different than the previous example. Let me put that all up there simultaneously for a second. So your task in finding an average rate of change over an interval is to first find the 2 points and then plug those 2 points into the slope formula, and then that's your answer. Okay, so here's one for you. Again, this is a very often missed test problem, so make sure you give this one a go. Pause the video, work this out, and then come back and see if you were correct. Okay, so let's check. Once again, we have an x1 and an x2 here. So our first point is x1 comma f of x1, which is going to be negative 2 comma f of negative 2. And then our second point is x sub 2, and then f of x sub 2, which in this case is negative 1 comma f of negative 1. So finding these points, first f of negative 2 is going to be negative 3 times negative 2 cubed plus 2 times negative 2 plus 3. So that's negative 3 times negative 8 minus 4 plus 3. PEMDAS again, we do the exponent or we multiply. Negative 2 cubed is negative 8. So that's positive 24 minus 4 plus 3. So that's 20 plus 3, or 23. So our point here is going to be negative 2 comma 23. And then over here, f of negative 1 is going to equal negative 3 times negative 1 cubed plus 2 times negative 1 plus 3. So that's -3 times -1 minus 2 plus 3. So that's 3 minus 2 plus 3. So that's 1 plus 3, or 4. So this point, shrink this down. This point is going to be -1, 4. So we've got our x1, y1, and our x2, y2. We're ready to plug that into the slope function. So m equals y2 minus y1 over x2 minus x1. And that is, again, a formula worth remembering. 4 minus 23 over -1 minus 2. And so that's -19 over -3, which doesn't reduce. Let me just double check all my work here. Looks good. Okay. Now an application problem. So the formula for the distance traveled by falling objects on the moon, you know, on Earth it's -32 feet per second squared. On the moon it's 2.7 feet per second squared. So a significantly lesser force of gravity on the moon. And you can tell that when you watch the Apollo videos, the astronauts were kind of bouncing around because the gravity was so much weaker. So that's why it's different than the Earth. But it's d of t is 2.7 t squared, where d of t is the distance in feet and t is the time in seconds. Find and interpret the average speed of an object for the time interval of 1 to 2 seconds. So same type of problem. We're given an x1 and an x2. And so we want to find x1 and then f of x1. So that's going to be 1 and then f of 1. And f of 1 is equal to 2.7 times 1 squared, which is just 2.7 times 1, or 2.7. So that point is 1, 2.7. Now we're going to find x sub 2 and f of x sub 2. So that's 2, f of 2. And then f of 2 is equal to 2.7 times 2 squared, which is 2.7 times 4. And that's 10.8. So our point is 2, 10.8. Now we find the average rate of change by plugging these into the slope formula. X sub 1, y1, x sub 2, y2. So m equals y2 minus y1 over x2 minus x1. So that's 10.8 minus 2.7 over 2 minus 1. So don't rely too heavily on mental arithmetic, because you'll probably get it right the majority of the time, but calculator will serve you better, especially in a high stakes situation like a test. So 8.1 over 1, or just 8.1. So there's our answer, and interpret that. So it asks us to interpret it. What that means is the average rate of change between 1 and 2 seconds of falling on the moon is 8.1. So the average falling speed between 1 and 2 seconds is 8.1 feet per second. So if I drop something on the moon, then I wait a second, and then I observe its speed between that first second and second second. This is the average rate of change I would see. If I measured it exactly at the second second, at second two, I would get 10.8, but the average over that interval between 1 and 2 is 8.1. Okay, guys, so what I'd like for you to do for me by Monday is page 42 through 20 even. See you next time.